Yeah, so your 5 courses, I guess. 2 labs. You asked the question about how many courses I teach, right?
Yeah. How many of like the aerospace courses?
Yeah, aerospace. 2 labs, propulsion, orbital mechanics, and the design. So 5 courses. If you end up taking the advanced aerodynamics as well, I teach that one too. So 6 courses.
Just glad this isn't the last course we get to have you in.
What's that?
I'm just glad this isn't the last course we get to have you in.
Thank you. Me too. I'm glad I'm going to see you next semester as well. What's that? Yeah. I mean, well, I'm going to see him for the next semester. That's only, hopefully. I guess. I mean, you want to graduate, right? Yeah. No. Design course is not really a course. So essentially, you have to do a. It's a very as far as the information you're going to receive. It's a very general course. It's just project management type things. This is the things you're going to learn, and the lectures are going to be like 2 months, or even less than that. And most of your time is going to be spent on actually designing and manufacturing stuff. What's that? That's the idea. That's another missile by the rocket. Yeah, that's what we did for the previous course, right? What if you what? Guide the rocket. Guide. I mean, I don't think with the type of money we are going to give you for this, I don't think you are going to be able to build a guided rocket. Unless you make everything from scratch, which I don't think we can do. But the point is, we are going to make a rocket. Not an engine, but a rocket. Because building an engine is not an easy task. Right? Even the simplest engines. Okay, so let's go back to the. What is going on? Okay, let's go back to the course at hand, the propulsion course. The last thing we discussed was the pressure ratio. Let's see, which part of the... Did we talk about the efficiency of the Brayton cycle?
Yes.
Okay, we talked about the efficiency and also the backwards ratio, all of those things, right? I'm assuming we also talked about the cycles. Yes. Okay, that's good. And I can always go back up and see what needs to be discussed. Okay. So one thing that I want to know if you guys are familiar with is the relative pressure. Do you remember relative pressure from your thermodynamics? It's a thermodynamic concept related to entropy. Do we remember what relative pressure is? Have you even heard this term before? Yes. Those of you who have heard this term, who did you have your thermo with? Cyrus. Okay. So what do you remember? Nothing? What's that? 6 weeks. Oh, you took it in the summer? You shouldn't have. That thermodynamics you shouldn't take in the summer. I mean, yeah. I didn't mean anything about anyone. It requires a little more than 6 weeks. The same is true for heat transfer that I teach in the summer. So don't take heat transfer in the summer if you want to learn. Yeah, because, I mean, I guess I don't want to come in the summer teach. But we will talk about relative pressure a little bit later. So let's just, when we are working on the quiz, right? So let's just let go of that part. And just a reminder of the isentropic relationships. Let's go back to this thing we have here, the pressure, volume, cycle, essentially the pressure volume plot for this Brayton cycle. We have, if you recall, we had an isentropic process here, and then we had an isobaric process, an isentropic process, and an isobaric process again. So the idea is P2 and P3 are supposed to be the same, and P1 and P4 are supposed to be the same. But what is the relationship between the 1 and 2? Pressure 1 and 2. Essentially, the relationship is the isentropic relationship. Who remembers the isentropic relationships? So the idea is T4, right? T4, the ratio between T4 and T3 is equals to P4 by P3. And since we are going to use a lot of densities, I'm going to use P4 divided by P3, K minus 1 divided by K. The same is true for T2 divided by P1. It's going to be P2 divided by P1, K minus 1 over K. So in the future, we are going to use a lot of densities. To avoid any confusions, whenever I write this is referring to P, which usually stands for pressure. If it doesn't have this, it looks like this, it is a rho. It usually stands for density. Make sure not to be. The reason I do this is because a lot of people get confused in these courses, especially in aerodynamics, for whatever reason. So make sure you are clear on this one. And you can actually, relate this to the P2 divided by P1 or P1 divided by P2, K minus 1 divided by K as well. So isentropic relationships. I think we talked about this though. We talked about efficiency, you know. Let's go back to the efficiency. That's the next thing on the agenda. We have talked about efficiency before, so I think I'm just going to give you the one final equation for efficiency, which for a cold air cycle is going to look like this: 1 minus T1 divided by T2. Who remembers what was the biggest feature or the most important feature of a cold air cycle? Backwards work? You mean like it is reversible? Is that what you're saying? It's what is independent in the CP. So heat capacity is independent of temperature. So when you are dealing with the U and H, enthalpies and internal energies, you can actually write CPT or CVT, depending on whether it's enthalpy or internal energy, and you can take a C out, do the analysis. Okay, so based on this, and also the isentropic relationship we can rewrite this equation as 1 minus 1 divided by P2 divided by P1, the pressure ratio, K minus 1 divided by K. And you should always keep in mind that this pressure ratio in a Brayton cycle is a very important factor. It's a very important factor in Brayton cycle. So, and you're going to see later on that we actually are only going to work, I mean not only, but we are, instead of working with pressure, we are mostly going to work with pressure ratios in jet engine analysis. Okay? So, let's see. Is there any questions so far? We are going to solve an example on this, so hopefully everything will be cleared out. If you felt like it is rushed, and you will hear this rush thing up on the end of the semester. Right? I don't let the comments go. Okay, so I'm just kidding, of course. So let's talk reversibilities of the Brayton cycle and losses of the Brayton cycle. So where do you think these losses are? Let's go back to the TS diagram. What did the TS diagram look like? We have an isentropic process right? 1 to 2. Then we have an isobaric process, 2, 3. Another isentropic process, another isobaric process. That's the ideal Brighton cycle. So, where do you think the irreversibilities are in a Brighton cycle? Again, this is the TS diagram. This is not the PV diagram. That's why it looks a little different, right? Where do you think the irreversibility? Yes. So the isentropic, essentially the irreversibility, right? The system. Instead of an isentropic process, we are going to have an irreversible process. So we are not going to have this. We're going to have irreversible process, which is, we actually saw this in the Rankine cycle analysis as well, right? What else? What else do you think can be a issue here? Is it possible to have any pressure drop in the combustor? Yes. That's the combustor process, right? When you add the fuel and you have the combustion process. So the pressure drop is something that is always the case, always present, right? I guess you haven't passed any fluid mechanics. That's why you may not be familiar with the pressure drop phenomenon that much. But it is something, whenever you have air moving or any fluid moving, pressure drop is going to be one of the losses, right? But we usually neglect the pressure drop. Okay. So in reality, it is going to look like this. We are going to have an isentropic case, and then there is a pressure drop. It is not going to be as ideal as it looks. But this is actually going to look like this. But as I said, we are only going to focus on the irreversibility. So let's call this 2S, which stands for the station 2, as if the compression was isentropic. And then let's call this one 4S. This is the real form, 2. Right? So if the process was isentropic, then we would have been at this location. But in real case, the station 2 will move a little forward. So meaning that there will be some increase in entropy, right? Essentially, this means that for our turbine and the compressor, we are going to have a compressor and turbine efficiency, as we did for the pump efficiency and turbine efficiency in the Rankine cycle. But how should we calculate this turbine efficiency and compressor efficiency? How should we calculate that? Does anyone remember from the, or, yes? Instead of looking for the equation, just think of a concept of efficiency. What would it mean? When you are talking about the turbine efficiency, what does it mean? We usually get out less work from the turbine than we expect, right? So the ratio between the actual work divided by the ideal work, right? So it should be H2 minus H1, H2F minus H1. Right? No, that's the other one, right? I'm sorry. Yeah. Why did I say H2? So H4 minus H3, thank you. H4S minus H3. That's the turbine. H1 is the compressor.
I'm gonna use H1 and H2 for the turbine because
No, a 1 to 2 process is compression. Yeah, don't get confused. Like compression, generation. Let's call it turbine. Okay, what about the compressor's efficiency? How can we calculate the compressor's efficiency? No. Why? Exactly. So this is the other way around, right? In turbine, we are going to extract less work than the ideal case. In compressor, the same is true for pumps. It is going to require more work than the ideal case, right? So in compressor, we are essentially losing some work, right? Non-ideal case is to lose more work, right? Since the efficiency is always less than 1, a bigger value should be in the denominator, okay? The real case is the real value, so we are going to have H2 minus H1, H2S minus H1. And we have already, we haven't solved any problems with the efficiencies, have we? We kind of did. We did one, and then I told you how to do the other one, right? Okay. So that's it, the Brayton cycle analysis. If you know how to analyze a Rankine cycle or the Otto cycle, diesel cycle, you should be able to analyze the Brayton cycle as well. Okay? But the thing is, the last thing we really want to talk about here is how to improve the performance. Meaning that how we can increase the amount of work we are extracting from turbine, right, from the system through turbine, right? Or how can we increase the efficiency, meaning that how can we get more work for less heat, right? Or decrease the work in the compressor, okay? So, let's think about it. I want you to jump in. What do you think you should do? We already know how to improve, or hopefully you remember the different methods we use to improve Rankine cycles performance, right? We just talked about them. The same is true here, right? We're just going to talk about this. We are going to actually do some analysis on this later this semester, but for now, we are only going to talk about them, okay? So how can we, what do you think? What do you guys think? Okay, how would you apply that here? This is a regular Brayton cycle. You have the compressor, right? You have the shaft connected to a turbine. You have the combustor. 1, 2, 3, 4. How can we add an idea? Yes. Reheat it before where? Why do you want to reheat your gas here? You're moving in the right direction. What's that? Higher pressure, it's higher temperature in the combustor, right? So exactly. So one way to improve performance, essentially to decrease the amount of heat you need to put in, is to increase the temperature before a combustor, right? So we are going to add a process called a reheat process. Which is going to be just a regular heat exchanger. Hopefully we remember what a heat exchanger is, right? But how should we reheat this? Where is the excess heat that we are just going to dump out? Before the compressor here, but this is just ambient air if it's a closed loop system, right? Through the exhaust, turbine's exhaust. Exactly. So we are going to get the turbine exhaust, put inside this heat exchanger, and this process is called a regeneration. Pardon me? We essentially had the same idea in the turbine, right? But in a Rankine cycle. But the difference over there is that we're dealing with vapor and also liquid. Here we are only dealing with gas, right? Okay, and these numbers are actually going to be a little different as well. So this part of the process, the heat exchanger after the heat exchanger is called X. I mean, your book calls it X, but usually propulsion books just number them 1, 2, 3, 4, and 5. Just add the yes. Afterburners. Okay, so that's a very good question. We are using the turbine's excess temperature energy to heat up the gas that is going into the combustor, right? How do you think that an afterburner works? What do you think? It does increase the speed of turbine? Is that what you're saying? How would it increase the speed of turbine? Do you have any other opinions on this?
It was kind of like inject fuel into the exhaust or something.
So essentially, an afterburner is a second combustor. What do you want to say?
I was going to say a second combustion.
Is a second combustor, right? So that's also another way of improving performance, but it is not a regeneration process, right? Okay. So this regeneration process, in reality, for an ideal case, you want your h of x to be equal to h of 4, right? But it doesn't really happen. It may happen, but you need a very big heat exchanger, right? Which we are not going to have. So the ideal case is going to be different from the non-ideal case. Well, here, if you include this regeneration, you actually have to have an efficiency factor for it. And we're going to call it eta of regeneration. How can we calculate the eta of regeneration? Again, think about it. The idea was, you have to think about the idea behind the efficiency calculation, and also keep in mind that here, our ideal case would be to have h of x be equal to h of 4. So, based on this, how can we define the efficiency of the regenerator? So what was your name again? Zach. So what Zach is saying is that hx minus h4 divided by h4, right? What do you want to... So the energy change you are referring to, it should probably be the energy level difference between H2 and Hx, right? And the energy difference between H2 and the ideal case, which is H4, right? Does it make sense? So how much energy we have added to the system will be H2 minus Hx. That's the real case. The ideal case would be where Hx is equal to H4. So the amount of energy input is going to be H2 minus H4, right? Does it make sense? Okay. So our efficiency is going to be H2 minus Hx, or Hx minus H2, doesn't really matter, but it's going to be consistent. And that's it. So if in a problem I tell you that we have this regenerator, this is the efficiency, then you are trying to find the entropies for each step, you have to use this efficiency and H4 to find the H of X, right? Or the other way. I mean, you are either given H of X and you have to calculate H4, or the other way around. Okay. Any questions so far? And the second modification we can make is actually the afterburner you mentioned, but the name for it is actually a reheat. So we're going to have a combustor and a turbine. Then we're going to take this, whatever remains out of the exhaust of the turbine, we are going to take it to another combustor and put it in another turbine. For an afterburner process, we don't usually have a turbine, but it's going to increase the thrust anyways, right? That's a separate discussion. We are going to talk about discussion. How about the, we didn't talk about the changes in the TS diagram. How do you think this will change the TS diagram, the regeneration? So regular TS diagram, 1, 2, 3, 4, right? This is your regular TS diagram. How do you think this is actually, whenever we are doing this, we have to make sure that 2 is there. How do you think this regeneration will actually change the TS diagram? It essentially will add a new point, as Drew mentioned, on the way. So essentially what is happening is that it is going to help the combustor move from 2 to X, right? This is how much it adds to the performance, efficiency of the system, right? It is going to remove this amount of heat needed to go from 2 to 3. Does it make sense? So it doesn't really change the TS diagram, it just improves the efficiency. But what about this? So nothing is really happening to the compression process in a reheat. This is a reheat. We go from 1 to 2 to 3. So everything is similar. But then you are going to take the exhaust, combust it again, go to 5, and then 6, go back to 1. Does it make sense? So we're essentially adding a combustion process as well as a turbine process, the energy extraction process.
How far is that forward drop to go all the way to?
No. No. It doesn't go all the way.
Is it better for it to drop further?
Okay. Let's look at this. So we are compressing the air, then we are combusting it. We are essentially, if we extract all of the energy during compression, it should go to H2, right? But we can't really extract all of the energy through compression, right? So it doesn't really, but you want it to go further down. It depends. If you want to add a reheat, you don't want it to go further down. You just want to remove the part. It really depends on your application. For the simplest process, yes. Okay. Any questions? Okay. So we are going to talk about one more modification. Then we are going to do an example, hopefully close the thermodynamics book and move on to the propulsion, which is the thing that I'm very excited about myself. What's that? Is it? Unbelievable. Time flies. Okay, so we have to, I'm sorry, but we have to rush it. Okay, let's talk about the intercooling, which is the other process. So the idea here is that from 1 to 2 on a PV diagram, from 1 to 2, we are going to go through a adiabatic compression, right? That's the ideal case. And it needs some work. The amount of work it requires is going to be the area on the left-hand side of this diagram. That's the amount of work needed for this adiabatic compression. But if we actually, during this process, if we have actually cooling inside the compressor, we are going to achieve a higher compression rate with less work, right? I mean, we are going to require less work to achieve the compression, right? With cooling. So it is not a bad idea to include cooling in your compression. So that's why we are going to add a process to our system called intercooling, which essentially means that we are going to go to the compressor, and then it will come out through a cooler, which is also a heat exchanger, as this time we are removing some heat from it, right? And then goes back to another compression ratio. This is not going to be this ideal as having the cooling, but essentially what's going to happen is that your process is going to look like this. So the amount of work has decreased by this much in the intercooling process. And you can have different levels of intercooling. You are not limited to one. And then we are going to go to the combustor and all of the other phenomena. So in general, in reality, we have many intercooler stages, many compression stages, and then many reheat, many regeneration. All of these things are usually combined with each other. And the analysis of those type of cycles is a little, I don't want to say hard, but it is very cumbersome and time consuming. Because you always have to go back to the thermodynamic tables, look them up, come up with the values, come back. It's just the process is that if you know how to do a simple cycle, you should know how to do a complex cycle, but it will just take more time. That's the idea here. Okay? And let's see. What else? Just the isentropic relationship between the cooler. Something that you have to keep in mind is that from 1 to 2, we are not going to have isentropic process anymore. The isentropic process is going to go from 1 to an I for intercooler, and then from this I to 2, right? Let's call this C and D. So 1 to C is isentropic, D to 2 is isentropic, but C to D is not isentropic, which means that from 1 to 2, we don't really have an isentropic process. But we can come up with the relationships between for the isentropic parts. Tc divided by T1 is going to be equal to Pi divided by P1, K minus 1 divided by K, and T2 divided by Td is going to be P2 divided by Pi. And the reason we have Pi for both of them is that the intercooling process is an isobaric process divided by K. Td, yes, T of D, yeah. Which essentially means that your the compressor work is going to be divided into 2 parts for a cold air cycle we can rewrite the compression or compressor part work as this: CP of T of D, P2 divided by PI, K minus 1 divided by K minus 1. Essentially 2 stages for the compression, right? And keep in mind, in the intercooler, you are removing some heat, so there is no work done there, right? There is no work done on the system or done by the system. It's just a heat transfer. Okay. Any questions so far? Okay. So, if you go through, have you gone through the lecture notes I've posted? No. Not at all. None of you. Okay, that's disappointing, but that's all right. If you go through the lecture notes, you see there are a lot of material that is on there that we are not going to go over after this part, mainly because we are going to talk about them more extensively in chapter 2 of the propulsion book, right? It's going to start sometime next week, right? And so we are going to, this is just belongs to the thermodynamics of it, and whatever we have for the rest of this lecture notes. You don't need to read them, but we are going to learn them deeper, actually, in more detail later on. If there is no question, let's solve an example. The example I want to solve is actually on the Otto cycle. I want you to solve is on the Otto cycle analysis. It is also in the lecture notes. And it is a combined cycle. I'm going to actually, a dual cycle example. Have we talked about dual cycles? No? If you recall, the Otto cycle, we had an Otto cycle and a diesel cycle for a PV. For diesel cycle, we had, for an Otto cycle, it was 2 constant volume. Right? 1, 2, 2, 2, 3, 2, 4. This was the Otto cycle. Do we remember this? Yes? But for a diesel cycle, 2 to 3 was isobaric. A dual cycle that uses both Otto cycle as well as the Otto cycle is actually isovolume 2, 3, and then an additional isobaric process. So it has 5 steps. And these are, just keep in mind that these 2 processes are isentropic processes. Okay, so the example we are going to solve is actually is going to be based on a dual cycle or a combined cycle. And if you get a question from this part of the class, like the Otto and diesel cycle of the class, this will be your question. It will be a dual cycle, right? Because it essentially has everything in it, right? And yeah, so you should make sure that you are very familiar with this. Let me actually open the lecture notes here. Is this working for a second? Yes, of course. So you can see the actual question. That's it. This is the question. Okay? So it says at the beginning of a compression process of an air standard dual cycle with a compression ratio of 18. So we have the compression ratio. What is the compression ratio? Here, Yes, it is 18. Who said 18? You said it. Okay. It is 18, but what does it represent? That's the ratio between V1 and V2. Right? The volume at the state 1 and volume at the state 2. This is uploaded on Blackboard. You don't really need to. If you want to, you are welcome, but it is uploaded. I don't mind. I mean, sure. I just want to let you know. Yeah, the temperature is 300 Kelvin. That's for state 1. And the pressure is 0.1 megapascals. Again, for state 1. Pressure ratio for the constant volume part of the heating process. Where is the constant volume part of the heating process? 2 to 3, exactly. Is 1.5 to 1, right? Which essentially means that P3 divided by P2 is 1.5, right? And the volume ratio for the constant pressure part of the heating process, which is V4 divided by V3, right, is 1.22 to 1. We're going to determine the thermal efficiency and the mean effective pressure. We will talk about the mean effective pressure later as we get to it. But let's calculate the thermal efficiency. The first thing we need to do, what is the first thing we need to do? It's a thermodynamics problem. And in propulsion is thermodynamics. So whenever you are dealing with a cycle analysis, what is the first thing you need to do? Is to find the proper table. But I've already printed the proper table for you. So keep in mind, this is a gas cycle. So you have to look up the table that is specific to a gas, right? Not the vapor cycles, not the saturation cycles. We don't really deal with saturation in these gas cycles. Saturation, the vapor quality, all of those things that we had problems understanding belong to the Rankine cycle analysis, right? Here we have to look up a gas table. Okay, so, and the good thing about gas tables is that it can be only temperature based or pressure based, doesn't really matter. As long as you have one of the values, you should be able to look it up in the table, and you should be, which is also true for the saturation limit. Okay, so you are given the temperature at the state 1, and this is your quiz, so make sure to work on it. All of you have to work on it, and this will account as your attendance. We have already had 2 quizzes. Yeah, your attendance, right? If you are not, I mean, if you are in the class, you are attending class. But if your friends are not in class and they want to do the quiz, that's all right. They can just go. As long as, yes. Yeah, you didn't turn it in. I'm going to give you the attendance. I'm going to give attendance to everyone. So just, I guess, the first 2 weeks, it's all right if you do not attend the class. Okay. So, let's try solving this. We want to look up the temperature on this ideal gas properties of air table. That's table 822 in the thermodynamics book. In the propulsion book, it may be a different table, but the table will definitely be there. Okay? What is the temperature? The temperature is 300 Kelvin, right? So we just have to look up the 300 Kelvin temperature. All of you have the table in front of you. What are the values we have? We have the enthalpy, we have the internal energy, we have S naught, and we also have 2 parameters called PR and VR. That's a small v, or nu r if you want to be more specific. But what are those parameters? The relative pressure and relative volumes. This is something you should have learned in Thermo 1, right? But that's at the end of Thermo 1, I'm pretty sure a lot of people don't really get to it. And a lot of people don't really think it's important, so they don't really cover it. I see in Thermo 2, they already assume people know this, so they don't go over this. That's why I wanted to pause and make sure you know what the relative pressure and relative volume are. Think about it. What do you think the relative pressure means? If you look at the tables, we don't really have the relative pressure here in this. It is on the tables though, right? You have two columns. It says when delta S equals to 1, and then there is a 1 on top of 0, equals to 0, there's a 1 on top of 0. It says on the bottom of the table, it says PR and VR data for use with equation 6.41 and 6.442, which is the entropy chapter in thermodynamics book, respectively. Okay? No, but I like where you're going. So essentially, relative pressure should, based on its name, or relative volume, should give you the pressure relative to a reference value, right? That's the thinking, right? But, and that's what I was expecting to hear from you. But in this case, this is not really the case, right? This relative pressure is actually not a real pressure at all, not a real pressure ratio. This is related to the temperature at which, temperature between two states, the temperature ratio between two states, and that the significance of those two states is that the process between the two is reversible, meaning that the enthalpy change between the two processes is 0, right? So if you plug in you remember the equation we had natural log of T2 divided by T1 minus R natural log of pressures, right? As the process is 0, using that, we actually find the PR, which is the relative pressure, and that PR value, using the ideal gas law, we actually can find the VR value for it. That's the relative pressure and relative temperature. The reason we find those values is because it is going to be much easier for us to get the relative pressure for a specific temperature, right, and do all of the calculations for it. The good thing about relative pressure and relative volume here is that the ratio between the, for example, PR2 and PR3 is equal to the actual pressure ratio. So you don't really need to know the pressures to do this analysis, right? So essentially, it is removing a complexity from the system. Does this make sense? So as far as you are concerned, this is just a value you should read from a table. You should find the ratio using the pressure ratios here, or the volume ratios. You should actually find the relative volume for the second state, and then go back to the table, find the specific relative volume, find the appropriate temperature for it, corresponding temperature for it. Does this make sense? So these do not talk about the real pressure or real volume. It's just not a real physical thing. It's just a mathematical, I guess, game that is going to help us tabulate the temperature data. That's the best explanation I could give in 5 minutes. But if you are interested to know more, you can go back to your thermodynamics book, which I assume all of you have in your library, and read the entropy chapter. Okay, so what is the conclusion? The conclusion is you go to the thermodynamic table you have for a state 1, you have 300 Kelvin. You read all of the properties. You read the enthalpy, you read the internal energy. You don't need to concern yourself with the entropy there. But at this point, I mean later maybe, you read the PR and also the VR. Okay? VR here for this case is 621.2. So that will be labeled VR1, right? That's the VR of state 1. Okay? So, we have the V1 divided by V2. We have the volume ratio. The idea was the ratio between VR1 and VR2 is actually equal to the real volume ratio. So since we have the volume ratio and we have one of the VRs, we should be able to find the other VR, right? Does this make sense? So V1 divided by V2 here. Let me go back to the, where's my one? Huh? Yeah, go ahead. Interpolations. Yes, you are. A lot of it, exactly. But for my courses, as long as you do the first one, so I know you know how to do the interpolations, you can just guess the other values. Okay? Just take an average, whatever you want to do in your mind, right? I don't really, but because I want you to make sure that you know the interpolations, how to do the interpolations, but at the same time, it's just a lot of unnecessary extra work. But in a real design situation, you definitely need to do that. I guess in a real design, you don't use tables, you use computers for it. Okay, so does this make sense? So based on this, so we can actually find the VR2, and then when you find the VR2, which I do have here, the value for it, VR2 is going to be equal to 34.51, right? Based on this. So we have 621 point, what is the value, 0.2. You can find the VR2. Then you come to this table again. You look for 34. 34 should be 34 point what? 0.51. So it should be between 900 and 920, right? So for this one, you need to do an interpolation to find the correct temperature value, right, for this first one. Yes, I'm sorry. 880 and 900. That's correct. I'm sorry. You do an interpolation here, you find the appropriate temperature. You also read the enthalpy and internal energy. As well as the PR. Okay? So we have the PR2 now, right? And for PR, you have to do another interpolation, just make sure, because you have 2 data points, right? Does it make sense? 34.51. You go back to the table, you find that corresponding line, whatever that is, right? Using interpolation. And then you calculate the interpolated enthalpy, interpolated internal energy, and interpolated PR2, right? Okay, so this time again, the ratio between PR's relative pressures is actually equal to the ratio between actual pressures, right? We have for station 3 and 2 and 3, we actually have the pressure ratio, and we have the PR at the station, at the state 2. We should be able to find PR at state 3. So PR3 divided by PR2 is equals to P3 divided by P2. This is, you have found this using interpolation, right? We had this, oh, wait, I can write here. Okay. So this is equals to PR3 divided by PR2. PR2 interpolation, we also have this value. We should be able to find PR3. And then for the PR3, you go back to the table, you read whatever value you need from there. And for the rest of it, I guess I'm going to give you 15 minutes, 17 minutes to solve it. Is this clear on what we are going to do for these dual cycles? It's just essentially you are dealing with the relative pressures, relative volumes, as well as temperature. So it's just going back and forth between those two. And at each stage, you have to read the enthalpy and the internal energy, enthalpy and the internal. For most of the cases, we use the internal energy. Just only for one process, we are going to use enthalpy to calculate the heat input or the work output or input. Okay? Hopefully you remember. We already have those equations. So, what's that? Which values of P? So this again. So we read the VR1, right? And using that VR1 and this, we found the VR2. You went to the table. For that VR2, you found the corresponding temperature, T2, right? As well as enthalpy, as well as the internal energy, as well as a PR2. Okay? And all of these you have to do an interpolation to find. For this quiz, you don't need to do the interpolation. Just guess a random value, whatever, that is between the two. You'll get extra point. Whoever does interpolation and finishes in time, you'll get extra point. Huh? You already got this? Okay. Okay. And then to finish this, the answer to Karim's question, you get this PR2 divided by PR3 should be equal to this pressure ratio. You get the P3. For the next process, 3 to 4, we have another volume ratio. So you have to deal with the VR3 and you find the VR4, all of those fun parts. There is only one catch here, and that happens between process 4 and 5. But we'll get to that later. Let me actually tell you about that as well, and then I'll let you finish whatever you are doing. So at some point, you will find the value of VR4 and PR4 and all of those things. But for V4 and V5, we are not given anything. But we are not given any information here. How can we deal with this? Can we find V4 divided by V5? Let's actually multiply this by a V3 divided by V3. Okay? This is going to be V3 divided by V5 multiplied by V4 divided by V3. Okay? We already know that V5 is actually equal to V1. Right? This is an isovolume process. And V3 is actually equal to V2. So V4 divided by V5 is V2 divided by V1 multiplied by V4 divided by V3. These are the two things that is already given to us. Let's plug it in and find the volume ratio between 5 and 4. Is this clear? Or is this too much information? Yeah, I mean, it should be PR3 over here. You did find T2? That's... You have to speak up, I don't hear you.
So I just went to the table and used the closest number to find it.
That is closest number is not acceptable. You probably want to take a value in between, right? But for one, at least the first one, you have to do an interpolation. The correct way of doing this is interpolation, right? So for at least one of them, you have to do an interpolation. So I know you know how to do an interpolation, right? But for the rest of them, I don't really care. Whatever, you just use the closest value that comes to you, and the value that's in between the two values, not. Okay.
Once we got PR2, we get PR3, and then where we go from there?
Where do you go from there? You go back to the table, right? The table, you find the closest PR, and then you do the interpolation of those fun parts, right? Get the temperature, get the enthalpy, get the internal energy, and the VR. And once you get the VR, you can go one step forward, right? To get the VR4. And then you can find the VR4 divided by VR5. So essentially you can do the same thing for V5. And when you're done with V5, you have all of the enthalpies and internal energies for all of the states. The only thing that you have to be careful about is that in this analysis, in the auto strike and diesel analysis, we don't always use enthalpy. Most of the time, we actually use internal energy because of the fact that it's either, sometimes there is no work done, so internal energy, a combination of the two. That's a very educated guess there. So you're stuck between the two numbers. It is closer to one of them. You choose a value that is closer to that one, right? It shouldn't be a guess that is out there, right? It should be an educated guess, okay? I just want to make sure everyone is clear on how to do this. Yes? Sure? You have to speak up. It's John, right?
Yeah. Does the fact that V1 is V5 not also mean that VR1 is VR5?
No, we are always dealing with that. No, that doesn't necessarily mean that. It may be true, but the thing is, they don't necessarily correspond to each other. So. And based on the numbers I have here, it is actually not true. VR5 and VR1 are not the same. Again, because that speaks relative pressure, and we use relative volume, we calculate relative volume based on relative pressure. It's more of an energy term, right? It is more related to temperature. And as long as T1 is not equal to T5, you can't really say that PR1 is equal to PR5. Does it make sense? Because it is not a real pressure term. Again, so that's relative. We can actually talk about relative pressure and relative volume a little bit more if you want to. But again, at the end of the day, these are the values that are calculated based on the assumption that entropy is 0 using the entropy equation we had, right? The natural log of T2 divided by T1, all of those equations, right? So that pressure ratio over there that we have that's inside the other natural log is going to give you PR at that specific state, right? It's not a real pressure. I guess you have to go back to MO1 to understand. If you want, we can spend more time on it. I personally think it is not a valuable time. H5?
Because,
Yeah, let's go over it again. We can actually clean these. Sorry, okay, so not a very clean. So V4 divided by V5. What I did was by essentially only multiplied this by V3 divided by V3. This part is easy, right? So we're gonna get V4 divided by V3 multiplied by V3 divided by V5, right? This we already have, right? 1.2. V4 divided by V3. V5, look at this process. This is a constant volume process, right? Isovolume process. So we can replace it with V1, okay? What can we say about volume at 3 and 2? Volume at 3 and 2 are also the same. So we can actually use V2 divided by V1, which is 1 over 18 given to us, right? So this is going to be 1.2 divided by 18. Then you can find the VR5 from there, right? Go back to the table and find the values. So this is the type of question you will, if I give you a question on the exam on this, this is the type of question you will get on the exam, right? And I mean, it will be similar to this. But the point is, if you don't know how to solve this, if you haven't practiced it a lot, it will take you a long time. And you won't be able to finish the exam, right? So you just want to make sure that you are quick in solving these problems. Yeah, it is, yeah. There are like 4 other questions on the exam that you want to solve. You don't want it to be... Oh, I think we need to talk about the syllabus a little bit as well, because I just came about, I heard about a new piece of information that I wasn't aware of. So, I heard from the administration, or the department chair actually, that we are not allowed to give you an exam on the last week of classes. So these 2 sessions, or these 3 sessions, I think, we are not allowed to give you an exam. So I probably need to move your exam 3 to November 17th, right? What I'm gonna do probably is I'm gonna do the chemical rockets before the exam 3, and then do the combustion chambers after the exam 3. The combustion chambers part, we don't even need to do the combustion chambers. That's an extra step that I have included there, because Dr. Wan wanted me to include this, and the only reason he wants this to be included is because he is a combustion guy. So, and not that many aerospace engineers know combustion. I mean, it is good to know combustion if you take the course. It is definitely recommended. You should go and take the combustion course. But I don't know if we will have enough time to cover it. Okay? Do we know combustion? Is there anyone who understands chemical reactions and combustion a little bit? You didn't hear me? Is there anyone we were talking about combustion, right? Is there anyone in the class who knows a little bit of combustion and chemical reactions? Okay.
I mean, there might be something in there.
There might be something in there. Better than nothing, right?
The possibility that there might be something.
Okay. What's that? Okay. If you are interested in propulsion, you definitely need to take the combustion course. Okay, with Dr. Vaughn. And thank you, Vaughn. I'm pretty sure you know who Dr. Vaughn is. Okay, so it is 3:35. I'm hoping that you are done with your quiz. Please submit those as they will be counted as your. What's that? You got the H values? Okay. That's more than enough. I'm pretty sure not a lot of it. What's that?
On the back, is that how you get the work net?
That,
With the thermal efficiency?
we have the H3 minus H4, H4 minus H. Yes. Yeah. Now you want to do use though, right? Thank you.
I have H on the other side.
Okay. You have to speak up. I don't hear you.
What?
I don't hear you. You have to speak up.
Can I ask you questions about this after the class? Because I'm very confused.
Sure, definitely.
What'd you say?
Sure, definitely. Why aren't you wearing a mask? Make sure you wear a mask next time, okay?
I don't have COVID.
That's just the rules. That you want to follow the rules. Let's actually do this because I have a. What was your name? Joseph. I have a class after this. I have to go to a class. So if you want, we can meet tomorrow, sometime tomorrow, and go over this. Okay?
Alright. What time would you be free? Or where could I meet you?
Tomorrow.
I have a heat transfer class that ends at like 2:15. So I'll be here right after that.
What about before it?
Before it? I can be here before it.
What time?
Anytime. It starts at 1:15.
Let's do 12. Huh? 12 p.m.
12 p.m.?
Yeah.
Okay, here?
No, in my office.
Where's your office?
A117 300 Main Street. Okay.
117.
Main Street. Main Street.
Do we still have labs at the regular time?
Yes.